headed into the 5th day. I hope you enjoy the week here. And yeah. So our next plenary speaker, Wanli Yang, actually my colleague, will tell us a little bit story about the MRICs in battery research. So he's a senior scientist at Advanced Light Source, Berkeley, and he received his PhD in the Institute of Physics in Beijing, Chinese Academy. And then he moved to Stanford as a postdoc and then a beam scientist at LS before he joined LS. So, and then he started actually at ARPAS, so actually people may notice his science paper on diamond dioid. And then when he joined LS, he became a scientist for RIX beamline 8. So he's going to tell us a little more story about that. He received the Middle Career Award actually for VUV in 2019. So, Wanli, it's yours.
Could you say that Uppsala? Just a moment.
Oh, yeah. Okay, so that's a little bit more program here. It's after Wanli's talk, and our next meeting site in Uppsala team is going to present a couple slides about their plan for next VUV. I think it's 26. So if you like to see what happening next time, stay tuned. Okay, Wanli.
Thank you, Jinhua. Thank you, everyone, to be here. So the photo is actually the advanced light source, or the probably about 100 of RIX maps in my talk. So they are all collected at the ALS, and many of you have visited there. If you have not, just for the view, you should do that. So I am
Wanli, your microphone is home?
Hello? Oh. Need to be close enough, sorry. So I am actually a member in the RIX program of the LS, and Jinhua is a program lead if you were here yesterday listening to his talk. So today I'm not going to talk about the instrumentation, so I will really focus on what we can do with soft X-ray RIX for battery research. And I also want to thank our organizers, Arnoldo and Tulio is over there, for organizing this very nice conference here, and it has been always a very warm welcome community of spectroscopy. With that, I want to mention first, all the VUVX techniques today, they rise from fundamental physics field. But what we should all realize now is the techniques have been mature enough these days to be used for many practical, extremely practical purposes. And take the talk today as just one example of what you can do with a powerful tool from physics community based on both the technical development and the understanding to see what it could do for a very practical problem here. Okay, so without much ado, I don't need to mention how important the battery is, so I will just jump directly onto what we thought we know and what we could offer. If we look at a super simplified model of a rechargeable battery, I think we all know what we have is there are two electrodes, and depending on charge or discharge, the electron is going through outside circuit, and then the ions going through the electrically insulating electrolyte going back and forth. So when the lithium ion going in and out one of the electrode, the electrons has to go in and out to balance the charge. That introduced the physical process here. So what happened is when you have ions going in and out of the electrode, it is the transportation or accommodation of the ion is relatively more of a structural issue. So that's why majority of the electrode, they all take specific structures, layered, spinel, and various kinds, because they need to accommodate the ions. And that is a topic the hot X-ray techniques has been contributed significantly, and neutron scattering too, to that topic. So if we think of the electrons, however, when the electrons going in and out of an electrode material, in chemistry language, it's called reduction and oxidation. But in physics language, it all depends on where is your electron state are, which one is close to a Fermi level. That will be the one to be filled up or to be pulled out, the electron state there. So this is a so-called redox. I will keep using this term in my talk. It refers to reduction and oxidation, but again, in physics, it means the electrons getting removed and injected from the electrode materials. So lithium chemical potential. So when you have the lithium, when you have the battery cell completely discharged, the potential will merge together. You put the two materials together, you get nothing. It's 0 voltage. But if you charge it, meaning you move the lithium from the cathode, the positive electrode, to the negative electrode, and they will open up this chemical potential, and then you open up the so-called open cell voltage of one battery cell. So in my title, there is a word called high energy batteries. So what is high energy batteries? You can see it from here. So high energy, there are two components in there. One is you need to have a high capacity. So how much lithium you can pull in and out of the electrode measured by the current, because the electron always go with lithium. That is a capacity. But the power of the battery cell also depends on how much you can open up this gap. This gap tells you what is the voltage you can get per battery cell. Under Tesla Model 3, there are 7,300 cells sitting under the car. So, but this is just one of the cell. How much you can open this up determines the voltage. Of course, you want a very high voltage over there. That means you need to pull a lot of lithium out from the positive electrode into the anode to open up this gap. That's the whole issue coming up that we will talk about today. So with that said, I want to mention there are so many problems that VUVX techniques could contribute to, not only on the electrode material, especially the surface and interface. Many of our tools are naturally surface and interface sensitive. That's not a topic of my talk today. And today I will focus on the transition metal-based oxide electrode, especially in the cathode side. When we try to open up this voltage, why we cannot get there. So why we still don't see a commercial battery that could really give us a stable cycle for 1,000 cycles with high voltage, and why and how we approach that. That's a focus today. And of course, with the transition metal oxide, if we try to really figure out the electron states, and all the VUVX tools comes in, and we want to see elemental sensitive of those electron state of transition metal and oxygen, and those fall into our domain here naturally. And that's a focus of today's talk. Essentially, transition metal oxide with electron going in and out through this redox process. So on the transition metal part, I think we all know that is relatively a easier question for our community here. The reason is the transition metal 3D states. I'm talking about 3D transition metals in particular, but I will have some 45D transition metals. the electron state, they are very much localized. So in both experiments and in theory, they are relatively easier to handle, meaning experimentally the features are much well defined, and in theory, it's relatively easier to approach them. So of course, this is Frank de Groo's book. It's like a dictionary. You can always check with whatever 3D transition metal spectral you want to refer to and check. And this is just one of the examples we did many years ago as a demonstration how powerful just the X-ray absorption of lithium iron phosphate. This is a well commercialized battery material. When you go through this charge and discharge, the iron going from fully discharged to the charge, and the whole spectrum change vividly like a beautiful butterfly. But be careful, this is not just like an intensity going up and down. This peak is not this, it's actually on this shoulder over there. So it's a complete change of the spectral line shape that gives you the opportunity, if you take all the knowledge from this community, and you can easily just quantify what is the oxidation change, and you can quantify all the way down to per molecule electron transfer number. So that corresponds to how much of your charge and discharge current is compensated by which transition metal element, changing from which state to which. And the quantification could be easily done through just a linear combination. All those dotted lines are our simulation, and then the solid lines are the experimental data. You can tell how precise this could go to. So this is just a quick flash on the transition metal. If we go one step further, we found some very interesting fundamental physics concepts that affect strongly battery performance, and this is one typical example I always like to just mention. It's a material from Sharp, USA. They have an R&D lab doing battery research. It's a material all with iron in there, surrounded with either carbon or nitrogen in octahedral configuration. So it's supposed to be just iron redox, and you're expecting just one voltage plateau if you put it as a battery cycle. This is again the cycling curve. This is charge and discharge. But you see, obviously there are two voltages there. And why? So if you take just the X-ray absorption of the iron, when the iron is surrounded by the carbon and nitrogen, they have very different crystal fields, so they take different spin state. So the iron surrounded by the carbon will take the high spin state, and the iron surrounded by the nitrogen will take the low spin state. And if you look at how those electrons occupy the T2G and EG level of the octahedral, you can tell like, if you want to have an electron coming in, obviously it prefers to sit over here instead of coming here to repel, competing with the Coulomb interaction with all the electrons over here. So it's a lot easier to have an electron filling here, meaning on the discharge, there will be one plateau here, a difficult plateau over there. So a fundamental physics concept of the spin configuration completely determined what is the voltage of a battery cell. So to make it more practical in the industry, it has been a puzzle to have a trace amount of water in your material, and it will change your battery voltage completely. So this is another example. If you have the water in your electrode, it will behave like this. This curve is the electrochemical performance on the voltage versus, again, the current, meaning the capacity. But if you if you dry out your material, and then it becomes a much preferred, the industry really loves this kind of charge and discharge curve instead of two plateau. And why? So once you understand the fundamental physics, you suddenly realize the water intercalated into the material just change and disturb your crystal field. And then your spin state change, and then the different elements, they will mix up and they change completely your electrochemical profile. So the fundamental physics went again. So the industry people, I think when we talk to them, they really amazed. I'm like, wow, we never realized a very far away from us a fundamental concept of electron spin state dominates so much on how the voltage behaves in a battery cell. So of course, there are cases, most of the cases we can resolve transition metal state by just X-ray absorption. Sometimes you need to do more careful experiments. So, but in some other cases, if the transition metals go beyond the conventional range, and then we probably will have a problem with just X-ray absorption. This is another material from a company. It's a startup company in Silicon Valley, and this is the CEO. We chat in one of the chemistry conferences. So what they found is there is a manganese redox-based material, and the material could be reduced to the very low voltage. So I said the high voltage battery cell, you can push this up. That's the main topic after. This is the last example before we jump to oxygen. Or you push down the potential here. So this material push down, it could reach very low potential as a negative electrode. And the benefit of that is in commercial battery cells, these two materials, they are always completely different. Typically, one is graphite-based, the other is transition metal oxide-based. But if you can process both of the electrode in the same type of material for industry, that's a huge gain because it reduces the material processing, the cost significantly. So this company actually is shooting for directly the low-cost batteries. That's why they care about a transition metal-based anode to reach the very low voltage. However, the material itself, it was already manganese 2+ state, and if you reduce it on the X-ray absorption, you really don't see this is a charge and discharge. You barely see a little difference here, and then we want to go a step further using a RIX map to see whether we can really differentiate the charge and discharge. So here I said I will not talk about the instrumentation much in my talk, but I do want to mention one thing that we do have lousy resolutions. If you have heard the talks in the previous days, and our resolution is very low, only about 1,500 resolving powers, limited by resource and also real estate, the space at the LS. Although we are improving in the next, hopefully, 1 or 2 years, but we do have the benefit. Our spectrometer covers 400 to 450 EV of the emission energy in one single shot. So we can pull out all those channels from the so-called partial fluorescence yield, inverse partial yield, core-to-core decay. Everything shows up simultaneously. That's a top. I don't have it in this talk, but it's just something keep in mind. When we go very high speed scanning through the absorption edge, we can pull out all those kind of information by one map coming out here. So now if we just focus on in physics, we call it the RIX regime of this feature, and I just rotated the absorption spectrum over here. And in the RIX map, you can see the contrast between the two. The reason you don't see much here, only a tiny little difference, is if you integrate all those signals over, the difference is sort of smearing away. And to understand this is also very straightforward because those states are well known in physics community is from the D to D, the 3D occupied to unoccupied electron excitations. So those D to D changes corresponds to the occupation of your electrons, of course, and again to the spin state. And these are the low spin state of the manganese 2+ originally, and 1+ will have 6 electrons over here. So this is a fingerprint of the 3D in octahedral configuration low spin with all the 5 electrons occupied. So majority of the D to D is from the T to G to EG. While if you remove an electron, you will have extra T to G occupied to T to G unoccupied excitation. That's why you see like 2 lines, and the other one is more concentrated to the higher energy DD excitation. So yeah, so this is again a demonstration on if you go beyond the conventional range of some state, that is very hard to see through the absorption. And also XPS, we also tried, it's very hard to see the difference. And RIX is able to pull out the information along another dimension, which is the emission energy, of course, to tell you the difference. And also the other funny thing is manganese 1+ was predicted in a paper written in German about a century ago. It was never verified until this point, and you can see why. It needs a VUVX powerful tool in order to really see that. So with that, I really want to spend all the leftover time going to the oxygen side. And the reason this becomes a very important topic is, again, I said we are talking about high energy batteries. I was saying to drop this, but majority of the effort is really to increase the voltage of the transition metal oxide-based positive electrode. And when you have the voltage going up, you are oxidizing the oxide. You are oxidizing it really above the conventional range, meaning if you synthesize a material, and you can synthesize with all different oxidization state and all those, but all of them are bounded together by the Madelung energy, right? So its ionic interaction is so strong, so they bond together. However, electrochemical process is a crude process that you can just drag the electron out, whether the system likes it or not. So it really drives the system into a different fundamental ground state. So that is very important because, as I said, the key thing here is which electron state you are working with when you go to the high voltage. And the question in chemistry language it triggers is always a straightforward question is the electron is pulled out from transition metal or is it from the oxygen? And this is also a safety issue. If you pull out the electron from transition metal, is relatively stable structure, and then cycling is more stable and things. But if you pull out from oxygen, all different kind of structural collapse and release oxygen, I will talk a little later, all the safety hazard also comes in. So that's just a very general impression on the thought. So it's very important to figure out what's really happening when you go to the high voltage, and of course to understand why it doesn't work. Again, on the absorption, if we look at the reference compound, it is seemingly promising because if you look at the oxide state, comparing with the pro-oxide state, you do see, especially those pre-edge regime over here, the peaks are sitting at very different energy. However, if you look at a transition metal oxide, that's a whole another story because everyone here will know the pre-edge regime exactly in this energy range is actually dominated by the 3D characters through the hybridization. And this is at that moment, we call it a killing experiment to kill tons of papers because many papers are discussing the pre-edge change of the oxygen K to talk about, oh, oxygen is going through redox process, but it's really just a hybridization effect. So the reason is this lithium iron phosphate, I showed you that beautiful butterfly, so that is a purely iron redox material. There's really no oxygen redox involved here. But if we look at the pre-edge of this oxygen K spectral, you see from the discharge to the charge, this is so far the strongest change you can find in any battery materials. However, it's also a material that has no oxygen redox. It sounds very ironic, but that's enough to kill the idea using the pre-edge of a transition metal oxide to determine whether your oxygen is really going through oxidization and reduction process. So the question is, of course, how to differentiate the oxidized oxygen state you want to see from the transition metal character hybridized into the oxygen spectrum over here. So with that, I should mention one thing first. So that is in the battery community, it is well known if you charge a transition metal oxide-based cathode to a very high voltage, meaning typically beyond about 4.3 to 4.4 volts, depending on the material. And you will see the release of oxygen from the material. And this release of oxygen, there could be just oxygen gas. That's what I'm showing here. This is lithium nickel oxide. LCO is lithium cobalt oxide. Those are nickel, cobalt, manganese compounds. There are all kinds of different oxide materials. If you cycle it up to beyond, for example, 4.5 volts, and then you will see the rise of this is the oxygen gas coming up. I just almost, there are tons of paper. I just randomly pull out a recent paper by Gasser group, and it's a famous group working on this kind of technique. It's called differential electrochemical mass spectroscopy. So you will see the oxygen release from the material if you go up to certain voltage. However, you can see over here already the lithium cobalt oxide is doing really well. And sometimes we were amazed. Lithium cobalt oxide is the very first commercialized battery positive electrode 30 years ago. And it remains the highest energy density up to this moment. After 30 years of effort, it still has the highest energy density. And if you look at the gas release here, obviously this is not a very good thing. You have gas release. It's completely irreversible. So that's not something we want to have. And lithium cobalt oxide, the very first positive electrode, they behave almost like the best of the best in this whole set of material. I'm not sure it's Professor good enough was just lucky to hit this, or we are just doing such a lousy work after 30 years, we just couldn't break this through. So anyway, keep in mind, there is oxidation of oxygen in the form of oxygen release, completely irreversible. But in the meantime, if we pull out the Rix map of this is transition metal oxide in a famous compound. I will come to what this means also. But it's in a compound we know there is oxidized oxygen. And then you will see some individual features close to the elastic peak and also very strong like an island of signal around 531 excitation energy over there. And in the integration of X-ray absorption, you typically see, depends on what kind of transition metal, sometimes you see a peak, sometimes in this case, I intentionally choose this material, of course, you just show a value. You don't really see the signature in the X-ray absorption pre-edge again. So in order to verify, this is one of the features we really want to see. So we went through several materials, and this is one material. It's for a sodium battery material. It's a material that does not show the oxygen release. I just showed you most of the material. So this is like lithium cobalt oxide. So they are fairly stable if you charge it to relatively high voltages. So meaning if the oxygen is getting oxidized in this material, it should be contained in the material. So, and then we do see this kind of feature with a red arrow point to where you charge and then discharge. So you see the feature going up and down. If you count the total intensity, you just integrate the intensity of the feature, and those are the dots plotted on here. If we calculate the ratio of this comparing with the estimated oxygen redox, there's a perfect match. Because we can see the magnet, I said transition metal redox, we can quantify. So we just get that deducted and we can match the capacity. The ratio shows an excellent agreement. So that indicates this kind of feature going up and down, it does indicate a reversible, to some extent, the reversibility of the oxygens going oxidized and reduced. On a so-called lithium-rich compound, as I said, I will come back to this material later. We see the same thing, however, the ratio never match again. And why? Because previously, we have the oxygen release. So part of the oxidization of the oxygen, they could come as an oxygen gas or radical oxygen release from the material, but part of them are contained in the material going through this charge and discharge process, which is seemingly what we prefer to have. And this is a typical example by using a tool like RIX and combining transition metal redox and oxygen redox. You can probe by looking at the feature going up and down and also the oxygen release through the DAMS experiments. You can clearly differentiate all kinds of oxidization process, and the oxygen release, as I said, is really the bad part. It's zero reversibility, and then when you charge and discharge, this is only 10 cycles, the first, second, fifth, and 10th. The capacity just drops down because the oxygen release is not really reversible at all. And majority of what you can see by RIX in the oxidization and reduction of the oxygen, however, is fairly reversible. But I will come back to this topic again. It's still not good enough. So when we have this comparing with another material, I said, has limited oxygen release, what we see is the capacity itself is much better because we don't have the oxygen release. The reversibility of the oxygen redox is much better. So the fade out of the capacity comparing with this is a lot better. However, we see another problem here. That is this is the charge voltage. This is the discharge voltage. The difference over the charge and discharge is huge. So what that means for a battery means you need to pour in a lot of power to charge up your battery. But when you start to use it to discharge, you drain out much, much less power. You're just wasting tons of energy. And that already indicates there's an energy barrier in there. And that's the so-called voltage hysteresis. So remember this name because we are coming back to that. So with that said, I think I showed you on the, just look at the observation itself. It seems like we get some good sense on a sort of reversible oxygen redox when you cycle the oxide into the very high voltage regime. However, we also see, although some material shows much better reversibility, some shows worse reversibility, but the one even with the better reversibility shows another issue called voltage hysteresis. So it could be thermodynamic, it could be kinetic issues. So none of those seems to be really commercially viable, honestly speaking. So the question for us doing spectroscopy, I should say I'm not really a battery guy. We're really doing fundamental research on battery materials. So what we want to solve for the community are really some deeper question. That is, what is the fundamental nature of this feature? And that's related, what is the material origin of that? And hopefully what we can see is whether there is a viable channel to approach the high voltage operation of a battery, especially for positive electrode. I think I forgot to mention the positive electrode is really the bottleneck of this because the anode part, the graphite anode is very close to lithium metal already, meaning it's almost reached the limit of how low you can get to the anode. That's why all the attention is on the positive electrode to increase, to oxidize it. So, and of course, the ultimate goal is if we can guide the finding of the materials to a commercially viable high voltage cycling. Of course, I don't have the answer here. As a matter of fact, if anyone has an answer to this, he or she will never stand here giving a talk. He or she will be busy becoming a billionaire now. So, okay. So, but we'll try to get to the fundamental part. So, on the fundamental nature of this, at this point, I should mention the general background in the battery field. So, there are 3 models on this oxidized oxygen form or on this oxygen, so-called oxygen redox concept that is dominating almost the whole battery field. very few groups do not agree with you see like 99.9999% of papers coming, they all follow the trend of those three main domains. So one is Professor Bruce in Oxford. So they previously had this so-called localized oxygen holes, but recently they have been pushing out a concept to say the oxygen redox itself is by forming and decomposition of oxygen gas molecule that is trapped in the material. So, and one of the critical techniques used in his work, I believe is done in both the Swiss light source and also the diamond light source, is the high resolution rigs, and to resolve the vibronic mode of the features. I showed you there are features at 531 eV, and also there's a feature close to the elastic peak. We saw those like over many years. They always show up together. To resolve those vibronic mode feature and comparing with the vibronic mode of the molecular systems, it is very close to the oxygen gas molecule. So they concluded the redox, oxygen redox, is actually from the formation and decomposition of the oxygen gas molecule over there. So that is one that is, because it's more recent, so there are more people following this model now. And previously, and coexisting still up to today, is Professor Terscon in France. So they have been consistently talking about the peroxide or peroxo species formed by the OO dimerization in this. And by forming this peroxo species, and again, formation and decomposition, and then you can have a reversible oxidization and reduction of this process. What is interesting is those have been before when this Nature paper comes out, and then everyone follows Nature, of course. So before that, many years ago, there were quite some works already done on the molecular vibronic mode through the Raman. So you can see, I just quote almost randomly from, this is Professor House group in Japan at that time. So this is the Institute Raman, and if you look at the frequency of the vibronic mode, they see it shows up and then disappear when you charge and discharge. It all makes sense. Actually, the vibronic mode follows more of the peroxo species, more like a dimerized OO peroxide. That's a frequency. It still remains a puzzle to me today on why the rigs see different frequency than Institute Ramans, because it's all molecular vibronic mode here. Of course, nobody is talking about those Raman these days because oxygen gas molecule is more fancy in nature. So, and then there's a third domain of the model is more fundamental. So that is, if you have a specific material called lithium rich, as I said, don't worry about the name. I have another slide to explain that. And then what you will have is there's a specific local structure with lithium, oxygen, lithium, because lithium is highly ionic. Your oxygen orbital along the lithium state, they got highly unhybridized. So they got lifted up close to the Fermi level. So, and of course, if you try to oxidize, again, in physics, oxidization is pulling out electrons. You start to pull out the electron from those lifted up unhybridized oxygen state. And then you oxidize the oxygen. The issue with this model is, I think it's a beautiful model focusing on this local structure. But the issue is, it does not touch the point what kind of oxygen after oxidization it could be reduced, meaning this could be well oxidized with oxygen release, zero reversibility, and with of no use. So anyway, when we look at all these three dominating models, what we see here, there are two things. One is they are all talking about an unhybridized oxygen bonding formation. Either it's oxygen gas or it's peroxo species, or it's a pulled up unhybridized oxygen state. When you oxidize, they also form dimerization or form gas molecule over there. And then two is all this relies on specific structural configurations to have or not to have. It's not, it essentially tells us this is not a common or universal behavior that you are expecting from all kinds of transition metal oxide material. So let's see whether these are true. So on the material itself, so I will talk about the lithium rich now. So I have been keep saying this word of lithium rich. What does it mean is in a typical oxide positive electrode, like lithium cobalt oxide, you see in the formula lithium is 1 per formula. But if you have more than 1 lithium in the compound, you can see this like lithium cobalt oxide. It just has nickel and manganese in there. So if you have more than 1 lithium, 0.17 more, that is called lithium rich. The benefit of that is, I said, capacity is one factor. If you have more lithium, you will have higher capacity. So that's a lithium rich, how this is defined. And I've shown you this RIX map and with sort of the quantification of the intensity over here. And I also told you it does show inside the material this feature showing up and discharge going away. And I also mentioned this material has the oxygen gas release in there. So it's a combination of oxidization of oxygen. However, if we look at the RIX finding of the oxygen oxidization and reduction in the material, because all the RIX experiments were done in ultra high vacuum, of course. If it's released, it will not be here. And then what you will see is after hundreds of cycles, this is a material from Samsung, directly an industry standard lithium-rich compound. So when we cycle over 500 cycles, we will see the feature is showing up, disappear for hundreds of cycles without much of an issue. So we estimated the reversibility after 500 cycles, about 80% still retained. By the way, industry standard is after 1,000 cycles, the total capacity of your battery should not drop below 80%. So that's an industry commercialized cell standard. This is not there, definitely. However, there's another issue I just mentioned previously on the hysteresis of the voltages. Lithium-rich compound, however, unfortunately, have that issue also. You will see the charge and discharge curve. They are well separated, and the killing factor to commercialize this material after almost two decades of effort is actually the voltage drop. It's not the capacity. It's actually the voltage drop. That's a killing factor for industry because it's not only the power, the voltage, monitoring the voltage is also the signature. Your Tesla car could tell you how much capacity left and how much driving range you have in your e-bike or electric vehicle. If the voltage keeps dropping after every cycle, the industry just don't know what to do with that. So it becomes a killing factor there. So if we look into this material, on the first question I posted on the material origin of this oxygen redox, what we have over here, the reason you have more than 1 lithium in the compound is you mix this so-called parent compound of 2 lithium, manganese O3 in here. So if you mix this with a conventional lithium-1 transition metal oxide, that's how you introduce that. And if you look at particularly this parent compound, what it has is the lithium is taking 1/3 of the layer of manganese. So the lithium getting into the transition metal layer, that's why you get more lithium in there. So lithium in the lithium-2 manganese O3 is the reason this material is called lithium-rich. And lithium-rich is the flagship material to discuss the oxygen redox. So now you see the logic. It becomes natural to believe lithium-2 manganese O3 is the origin, is the material origin of the oxygen redox. And in fact, the papers with directly the title, Reversible Oxygen Redox, in lithium-2 manganese O3. And this is the RIX result. Once we have a tool to see whether there is oxidization and reduce in the material, and then we can tell whether there is really at least that kind of, meaning OO bond forming type of oxidization and redox. However, we measured this material from 5 different groups all over the world. We tried all different cells, switch lock cell, coin cell, pouch cell, all the names of different type of cells. None of those shows any signature of a reversible oxygen redox. And to make this even more crazy, what we found is because soft X-ray, we can measure the manganese redox pretty precisely. What we found is this after this charge process is purely just oxidization, oxygen release, radical oxygen surface reaction, all those. Right after this, it switch immediately out to the manganese redox. And the manganese redox, if you quantify, they can count for all those capacity over there. There's never oxygen redox in lithium rich. So of course the question is where the oxygen redox comes from. And then if we look at the lithium rich, and if we look at the lithium 1, this is a conventional compound with the nickel cobalt manganese, they show the same behavior when you pull it up to the high voltage. And this is lithium cobalt oxide. If I have time, I will jump to the lithium cobalt oxide at the end a little bit. So they all show up. So they don't really need the lithium rich configuration. This lithium rich is really not a requirement in the lithium battery cell. And the other thing is we measured nickel, cobalt, and various kind of compounds. Fundamentally, there's no limitation on where you are expecting this kind of oxygen redox, because eventually we'll go to the fundamentally, they behave all the same. If you highly oxidize an oxide, they will go to a different fundamental ground state, and they will change the overall configuration of oxygen transition metal. They all give you this opportunity. And if you look at different 4D and 5D transition metals, and you will see the appearance or not appear, this kind of feature also heavily depends on transition metal, meaning to have this is more like a fundamental transition metal oxygen topic instead of any structural type of choice over here. And then the nature of this feature, we did a bunch of, I need to be get a bit faster. So so we measured a bunch of reference compound. What we see is those are the pro-oxo species, all RIX maps. And I'm sorry for the busy plot over here, but what you can get from this is for all the pro-oxo species, we see this kind of feature, and oxygen gas. This is oxygen gas. We see this kind of feature. And then if you compare this kind of RIX features comparing with those pro-oxo or oxygen gas, but not the superoxo species, they show superoxide shows up at completely different position in the energy of those. So it seems like they do take exactly the same energy in the excitation and emission energy. So that indicates the feature we see seems to be a OO bonding formation, meaning it's a chemically defined oxidization of oxygen, not physically. So physically, when we define something getting oxidized, we look at the electron state, and then we see whether the electron left a hole. If you remember the talk by Thorsten, if we have a negative charge transfer state, for example, we pull out the electron from the ligand and you leave a ligand hole, in physics we consider that is a kind of oxidization in there. So the other thing is this kind of feature, we were fortunate to have it's an amazing set of material from Argonne National Lab. A typical lithium nickel oxide, what you will have is always a mixture of the nickel and lithium because of the size of the ions. They are very close. When you synthesize, it's very hard to push all the nickel in nickel layer, lithium in lithium layer. They always mix So, but they were able, I don't know how, but they were able to really make a perfect, almost perfect lithium nickel oxide. And then we watch how the feature emerge in a perfect layer compound of lithium nickel oxide. They cycle beautifully up to 4.8 volts. But this one, they decay. And this is with a little aluminum doping in there. And then you can see how this feature emerge. So when you have this antiside or you just dope it directly, you will see this kind of oxidized oxygen feature showing up. So this indicates when we have a feature like this, we admit it is very likely OO bonding formation, peroxide or oxygen gas molecule. That's what we see in the rigs. However, it seems to us more and more like a very local structure distortion, or if there is a defect, I mean, if you dope it, or so it's a structural related phenomena, very local structural related phenomena over there. So the other, to me, is a more important thing, that is OO bonding is a chemical definition of oxygen oxidization. As I mentioned, physically, we define the pulling out of the ligand hole as oxygen heavily involved in the redox or oxygen getting oxidized, you can call it that way. Then we measured all kinds of these physically defined oxidized oxygen. We really don't see anything on those features because those features correspond to OO bonding. And this is the CO2, we all know is highly covalent. It's very hard to say oxygen is 2- in a CO2 because they highly, and if you look at the negative charge transfer system, we measured a bunch of different thin film materials. We never see the crossing point and the elastic peak over here. They're supposed to show that kind of feature. So we do not see, if it's not a chemically defined oxidized oxygen, and again, those chemically defined oxidized oxygen with OO bonding formation, it seems to give us some inherent problem on the voltage hysteresis. And this is just a review of the Nature Energy, and I think from Professor Tarascon's group, they specifically talking about this theme, the killing factor of this kind of oxygen redox is on the hysteresis of the voltage, meaning there is either a thermodynamic or a kinetic issue over there. It was funny, last night, there was a new paper coming out from Nature Energy. It's specifically a topic trying to solve the voltage decay in this lithium-rich compound. Just last night, showing up in Nature Energy, and it goes with a very fancy two transition metal atom trap lithium site in there. They're helping a lot of work trying to approach at the lab level, going to the industry level, the cost and processing, all the complication comes in. So I think my time is up. I just want to mention one very quick thing, because I have been talking about lithium cobalt oxide, so I don't want to leave this as a whole. So this is one of the topics we have been working a lot with Tom Devereux at Stanford. We really try to solve this issue on what kind of oxygen redox is truly useful to have reversible, also not kinetic or thermodynamic issue on the cycling, on the voltage when you cycle for extended cycles. And then we did very careful both in situ cell working with a thin film company, and Jinhua has developed all kinds of in situ cells of this material, and also with ex situ experiments of both the oxygen and the cobalt LH rigs. Coupled with theory, we're trying to get something. So here I just want to show one very interesting finding. So that is the lithium cobalt oxide so far. You're still using that in your cell phone, the smaller scale batteries, because the smaller scale, you can afford to have a pure cobalt, expensive cobalt base, because they give you the highest volumetric energy density. Still, your cell phone and some of the laptops are still using pure lithium cobalt oxide. At the industry, all the lithium cobalt oxide, if you make it into a commercial battery, they never go beyond 4.2 volts. So 4.2 volts is almost right at the half of the lithium you can pull out. So they don't know why, but every time they tried with all different electrolyte additives, and when I chat with them, they went crazy on all kinds of possibilities to improve the voltage. It just never works. You go beyond 4.2 volts, bonk, cycling drops crazy after like only 100 cycles. So when we do a RIX map on those, what we see is it's a happy but also a sad coincidence. When we look at this kind of feature in the lithium cobalt oxide, we measure all the way up, step by step, to 4.2 volts. Nothing happens. Right above 4.2 volts, at 4.5 volts, this is 4.5. Boom, you see this feature start to show up. And then if you look at the cobalt, however, the cobalt start to change from the very beginning. It doesn't give you this kind of step behavior. At the very beginning, it's a well-defined localized 3D transition metal dB excitation. Right after you start to charge, the whole feature start to emerge to, if you remember what Thorsten was talking about, his negative charge transfer nickel LNLS feature, it start to emerge something like that. So it's a very intriguing observations. But we can see here, it seems there are some fundamental issues with the chemically defined oxidized oxygen state, trying to have that as a source of oxygen redox towards a high voltage. However, physics provide us other channels to go beyond that, and that's a story I hope to tell you soon in another time. So, and because it's still in the work at this moment. So I just want to very quickly summarize. I think the RIX by itself, if you follow me through this roller coaster, we have been happy, we solved the problem, and no, we're not. And then, maybe we could understand this, we found another problem. So if you look at the migration or the evolution of this, at least we try to push, the battery field has acknowledged very much the use of RIX, either a RIX, fast RIX map or a high resolution RIX. You have heard most of the RIX talks in this conference, and they appreciate very much, and this whole concept evolution revolves around soft X-ray RIX over here. I think that's all we should all be proud of this VUVX community. At the very end, I just want to mention Qing Hao and also Zheng Qing. They are the students and postdocs working with me on most of the content I'm talking about today. Okay, thank you.
Okay, thanks, Wanli, and I think the time's up. And but still, if there are one or two questions, we can get to it.
Well, thanks for the talk. I saw that you have the electrochemical cell there in one slide. Can you show to us?
The institute?
Yeah.
So,
and can you describe, please?
I thought I have.
Yes, you skip this. Yes.
So yeah, so I have 25 slides. I know I talk slow typically, so I have to skip this because of the time.
No.
So this is the institute cell formed by having, as I mentioned, the overall cell is sealed with commercial electrolyte in there, and we used the institute cell Jinhua talked about yesterday, well developed and optimized by Jinhua's group. And we seal the commercial electrolyte, and there is a Viton O-ring sealed with, on the surface, is silicon nitride window, 100 nanometer silicon nitride window, coating with an electrode, which is gold in this case. And then we have a collaboration thin film deposition film. They grow lithium cobalt oxide directly on top of this gold. And then we assemble this silicon nitride window, gold electrode, lithium cobalt oxide, commercial electrolyte, and we seal it up in this cell. And then we can do cycle, and the X-ray comes in through the silicon nitride window, and then we can take the data from the silicon nitride window. While outside, we can do the cycling over there. Yeah. So since you asked, however, I do want to mention, I was just chatting with Thorsten in one of the lunch times. So what we found is, this is institute data. The institute test of transition metal is fine because the transition metal only exists in the material you're interested in. All the results are very consistent with all the institute measurement we've done, but the institute data is of much higher quality. Provided, however, your electrode samples, your experimental samples are well protected and processed, meaning absolutely zero exposure. So if you expose it to the atmosphere, the humidity effect, they may change. But if you are careful by making all those electrodes stop at different level, try to maintain the state of charge, they are completely consistent. And oxygen, I didn't even show those are ex situ oxygen, sorry. So I didn't show the oxygen because oxygen with the in situ is another disaster. So we always see other very strong signature from the oxygen from other like electrolyte. In the typical example, oxygen is everywhere. And then we see the change of the oxygen turned out to be radiation damage effect, and so I didn't show it here. So I think the in situ experiment, they are critical for many of the surface interface related phenomena. You've heard talks on those. In the battery compound, most of the cases, we actually prefer the ex situ experiment. It was much cleaner, and also the analysis is much more reliable if you compare it with the in situ test. Yeah, not all of them. It's really case by case, but that's roughly how we form this in situ cell.
Okay. Okay. Maybe one more question to the side, and it's John, and then yeah.
Thanks, Wally. You know, this is way outside my field, and I learned a lot about the chemistry and redox reactions at the electrodes or at the cathode in particular. But does the electrolyte play any role in this redox chemistry, and can it help to stabilize some of this oxygen chemistry at the transition metal cathode?
Excellent. So, John, I'm happy you asked this question. One thing I should mention is in academic field, majority of the works are done on the electrode. In the industry field, 90% of the R&D are on the electrolyte. So in every commercial batteries you are using right now, they have more than 20 additives in your electrolyte, and every company has different formula of their electrolyte, and they never even file a patent. It's a top commercial secret in there. So what it has is different additives will affect the interface formation between the electrode and the electrolyte, and that interface and surface, you are absolutely right, it affects the redox process. I know it sounds like, but they are linked. So what kind of surface does affect what kind of bulk redox especially on the oxygen. We also have other works, I really don't have time to touch all those topics, to show by just changing electrolyte, the oxygen redox behavior, they can be different, like to have or not to have at all. So there is really a correlation in there. It all goes to what kind of redox activities, whether they rely on the gradient of chemical migration to the surface, or they don't rely on those. So different redox could have different effect, but there are cases with very strong effect. Yeah.
Great. Let's thank Wally again.
Thank you.
Yeah. I think anyone who's interested can catch him in a coffee break, and he'll be here a whole day today too. So I think of what we have, it's Uppsala group, right? Who's presenting? Oh, Yuan. He's going to. Oh yeah. So he's going to tell us a little bit secret about what happened in 3 years in Uppsala.
Oh, wow. Oop. Yeah, so some of us get to present twice. So this is on, right? Yeah. This is where we're now in Brazil, and it's been a really nice conference. I had lots of nice discussions, and I hope you all had that. And in 3 years in Uppsala, we hope to welcome all of you and all of your friends. Preliminary, 22nd to 26th of June, which is roughly now. And this is the picture of the city. If you look in the schedule, I was scheduled for 1 hour after lunch, so I shortened my talk now to 35 minutes. No, I not. Those of you who don't know Uppsala, maybe not all people do, just a brief history. Whenever you write Ångström in your papers, you can think of us, because we have both Anders and Knut coming from there. Manne Sigbarn was an old legend from Uppsala, and his son Kai Sigbarn as well. Many of you have certainly read papers by Svante Svensson, Josef Nordgren, who has been mentioned here, Nils Mårtensson, and Hans Sigbarn, who happens to be the son of Kai Sigbarn. And for those of you who don't know, Uppsala is also the birthplace of electron spectroscopy, which we're quite proud of. Uppsala city is located in the northern parts of Europe, but still within easy traveling distance from Europe. If you're not from Europe, you will probably have to take a connecting flight, so these are your flight times. Luckily, once you land, it's less than 20 minutes by train to Uppsala, or you can take a bus or a taxi if you like that rather more. It's a quite small city, so it's nice and cozy. You will be living downtown somewhere, and with easy access of all your friends. Last time we had VUV in Sweden was 40 years ago in Lund, so it's nice to come back now 40 years later. As I said, you can go by train, and also from other countries if you prefer to go by train instead of plane, or boat. It's possible. It's not that cold in summer. It was 25 when we left, and here's some weather forecasts I pasted in from earlier, so it's about this weather, a little bit warmer maybe. And we hope to have a satellites meeting in both fourth generation sources and ultra-fast phenomena in Lund and theory in Stockholm. The plans for the next conference is that it's about the same price as here, hopefully a little bit cheaper. There will be a reception, and there will be lunches on site. There will be Swedish fika, which is very important for us. There will be some poster session with some drinks. And hopefully we can also provide free access to buses if you prefer to go by buses in the city. Housing in Sweden is not that expensive as you might think. When I looked online just a few days ago, I find private rooms for 50 euros. And up, of course, you can pay whatever you want to. There will be an excursion with a Viking-themed dinner and mead, for those of you who like to try out mead. And there will be a banquet in the castle, but those two are not included in the conference fee. The rest is, I don't know what. Now, yeah, where we will be. We will be in the Ångström lab, in this wonderful green glass building. And this is a new building. It's just 2 years old, I think. We will be using up to 4 of the lecture halls. They are modern lecture halls, so we can sit and enjoy Wi-Fi and so on. This is pictures of the lecture halls, you don't know. But we can actually have up to 7 different parallel sessions if we are hundreds and hundreds of people. But the goal is at least to have 3 different parallel sessions, so to add 1 more compared to what we have here. In principle, we can seat up to, I think, 500 people for one lecture. Yeah, so with that, we just look forward to welcome you in Uppsala in 3 years minus a few days. And these are sites. Wow, it's very laggy, right? That I hope you will see when you're there. Thank you.
Thank you, everyone. Okay. Great. So, well, we're going to take a coffee break and ask you about it. Okay, let's thank both Wally and Yuan.